See, we want to get f of xy, correct? And how could we get? We realized that this would be in terms of its Fourier transform. If you look at it, Fourier domain, if you look at it, if that is equal to f of kx comma ky, then what would be this multiplied with e power j times 2 pi kx times x plus ky times y dkx dky, correct? This is the case. So what we do as a first step here is, for example, you take change of variable, because there in fact you have, if you want to make use of Fourier slice theorem also, you have this for varying values of theta, and for each theta for varying values of rho. So that's what we change this transformation so that we could exploit the Fourier slice theorem. So to do that, let's say I am taking here kx equal to rho cos theta, ky equal to rho sin theta. And then this is something you are now quite comfortable with, I guess, would be equal to dkx dky would be equal to absolute value of rho d rho d theta. Okay. And this f of xy, you could now write it as, you vary, for example, I want to vary, if I'm varying r from minus infinity to plus infinity here across this. Okay. If I am doing that, then if I just cover this distance, then that's good enough, isn't it? Theta is varying from 0 to 2 pi. Rho is varying from minus infinity to plus infinity. F of kx will be equal to now rho cos theta, ky will be equal to rho sin theta, e power j times 2 pi times rho into x cos theta plus y sin theta. Okay. And then what here? What will you get here? Absolute value of rho d theta. Is everyone with me so far? Is
Yes,
this
sir.
fine? Okay, good. So then from Fourier slice theorem, we have already seen that if you have, for example, an object for which I am taking a projection which is taken at an angle theta, I have the profile of it. This is my f of xy. This is x. This is y. Okay, this we are calling it as x prime corresponding to this, and that angle will be the same thing. So this we call it as g theta of x prime, and to that the one dimensional CTFT we were calling it as capital G theta of rho, and this two dimensional CTFT of it we were calling it as capital F of kx comma ky, right? Now how are these two related? G theta of rho is equal to f of,
F of rho cos theta, rho sin
that's
theta.
it, rho cos theta, rho sin theta, correct? This is our Fourier slice theorem. We have done it enough number of times now, right? You take that result here now, because see, all we have is projections. So that's why we are trying to write everything in terms of those projections. So now what do I have here? F of xy equal to theta varying from 0 to pi, rho varying from minus infinity to plus infinity. And let me just write this a bit earlier here. Absolute value of rho into g theta of rho into e power j 2 pi rho into x cos theta plus phi sin theta d rho. Okay, let me put it in one bunch here, and d theta. You could see that I could replace this with x prime here. Okay, because hope you remember here, this x prime, if you look at, this is your x prime. So x prime will be equal to x cos theta plus y sin theta. So yeah, this is in fact equivalent to theta equal to 0 to pi, rho varying from minus infinity to plus infinity, rho into g theta of rho into e power j 2 pi rho x dash d rho, right, into d theta. Now what is it equivalent to? This one is equivalent to, It is the inverse CTFT of what?
Rho times 0.
This is the inverse CTFT of this function, right? Now, what is it that we have and what is it that we need to compute? You have g theta of x dash earlier, right? That CTFT is g theta of rho, correct? That's what we had earlier itself. Okay, now you ignore absolute of rho for time being, okay? Then what does it mean? Theta varying from 0 to pi. Can I write here g theta of x dash then? So if this is not there, okay, this expression is equivalent to finding out g theta of x prime. So what is happening here? What you are doing here is you are varying theta value. That means this projection angles, you are varying it, and then you are summing up all projections together. And that is what is giving you f of xy. For a moment, you ignore this part and now come back and take the original one now. What is it equivalent to multiplying it with magnitude of rho? You have a function, g theta of rho is there. This I am multiplying with rho. What is it equivalent to? What is this operation equal to? Which kind of filter is this?
Low pass.
Are you sure?
Mm.
What do you mean by low pass filter? What it should do? Can you draw there how it looks like? Does it not look something like this? Magnitude of rho. How would you decide whether what kind of filter is this?
High pass.
Yeah,
High
you
pass.
in practice you put a cutoff here, so you could think after that you make it 0, but this is equivalent to high pass filter. So here you are multiplying here, which should be equivalent to, in the time domain, if you look at, this is equivalent to convolving your gt of x dash. Okay, let me call this function as, let's say, h of rho with h of x dash. So whichever is the inverse Fourier transform of this function, let's call it as h of x dash. So if I am going to convolve my, so this, what I have inside here, this function is equivalent to f of x comma y is equal to, theta is varying from 0 to pi, h of x dash, okay, convolving with g theta of x dash d theta. Is that fine?
Can we interpret as like when we take differentiation in time domain, we get this rho factor, I think, in the frequency domain.
Yeah, that is also correct. Very good. That's also a high pass filter.
Yeah, so the differentiation is basically taking gradient, right?
Right, correct. So that's a high
So
pass filter. See, just
yeah,
look at
so
this way. See, as you are increasing rho, for higher values of rho, the gain is more, right? For low values, the gain is less. Okay, then let's try to get some interpretation for this. Let's write g equal to g theta is varying from 0 to 2 pi x cos theta plus y sin theta, because one confusion you might be having is on one side I am talking about x comma y here, and on other side I am talking about x dash. That could be something which is making it slightly difficult. So let us look at it in this way now. So this is what we are doing. F of x comma y. This is what is there. Very carefully pay attention here. Suppose x cos theta plus y sin theta is equal to some constant r. You assume that x cos theta plus y sin theta is the parameter that you have inside. Suppose any set of x comma y, okay, for a given theta, assume that I am taking for a particular theta, what will be the set of xy points for which x cos theta plus y sin theta is constant. See, for a given x cos theta plus y sin theta, this whole value inside this integral is constant, is it not? Now, what would be the locus of all points x and y for which x cos theta plus y sin theta is equal to, let's say the constant is r. Can you tell me that?
so theta is also constant.
Yeah, for a given theta. See, what I would like to see now is I am varying here x comma y. I will take a particular value of theta. Okay. So cos theta, sin theta, I know there for that theta. Now, what I would like to know is what is the locus of all points of x and y for which, let's say, x cos theta plus y sin theta equal to r. R is a constant. Okay. Theta is a constant. Now I would like to look at all points of x and y. Where will be all those points? Can there be multiple points for which this equation could be satisfied?
Straight line.
Right. Can you tell where that straight line would be? Very good. That's a straight line. Have you ever seen this guy earlier, particularly those who have done a computer vision course? R equal to x cos theta plus y sin theta.
Half transform.
Half transform.
Very good. Very good. Correct. What is R here?
Distance from origin.
Correct. What is theta here?
Angle.
Correct. So those of you who have not done this course, don't worry. You first write a simple equation of a line where you call this as x-intercept is A, y-intercept is B. If I give you those two, how do you write the equation of a line? I give you x-intercept and y-intercept. How do you write the equation of a line?
xy plus y by b equal to c.
Correct. Now, I would like to
Equal
get
to
the A and B values. Okay, I know this is R, this is theta. So first you take here, for example, cos theta. All I want to do is now express A and B in terms of theta and R. Okay, that's what I would like to do now. So cos theta equal to adjacent. So this is 90 degrees by the way, and this is 90 degrees. So cos theta adjacent line is R by diagonal is A. That implies my A equal to R by cos theta. And similarly, if I take sine theta, let me take here. So this is sine theta, opposite side is this, that is R, and diagonal is B, right? So that implies what you would get here, x by R by cos theta. So x cos theta by R plus y sin theta by R equal to 1. That implies R equal to x cos theta plus y sin theta. Again, pay attention carefully here. I have an object. I took a projection of it. I got a profile here. This is my x dash. This is my theta. What it is going to do now here, while you are integrating from 0 to 2 pi for all f of xy, for a given f of xy, whichever value is here, you give that value to all these points in the xy plane here. They all will have same value here. So let us call this whole function inside as b theta. Theta equal to, let me write it as f of x comma y equal to, theta is varying from 0 to 2 pi. Let me call after the convolution what I am getting there as b theta of xy or b theta of x cos theta plus y sin theta, okay, d theta. Okay, so this part, let me, I'm just calling it with b theta of xy. Okay, so what is happening here is when you are computing for f of xy for various values in the projection, whatever you have here, that same will be, it is called as smearing. You give the same value to all f of xy which are there, this being r and this being theta. Is that clear to everyone? For a given theta, okay, so you take that and then you vary this r value here, and all these xy points at the end of this integration, okay, you forget about this integration, just you look at this. Okay, forget it, just a given theta value. That means one projection. For a given theta means for a given projection. How do you get f of xy values? You just need to propagate those points back. That would give you, if you ignore this integration, that would give you these points. Do you agree with that? See, you got this equation, which is in terms of x cos theta plus y sin theta. Okay, this is the only variable here. For a given theta, we figured out that all f of x comma y which are there on this line would get the same value. All I am now trying to see is, okay, instead of assume that this is also g theta of x dash convolved with h theta of x dash. I did, okay, h of x dash, whatever it is, I did already this. And then this is my b theta of x dash. I have it to find out. See, we have projections and we want to find out f of xy. The interpretation we could see here is this is equivalent to where will all these points are there. That's what we figured out. That is there at an angle theta here. And for varying values of r, this would be, for example, varying that will be equivalent to distance. This is distance is r here as you move on here. For each value of r, you just propagate them these values here. That's what you would be assigning for a given value of theta, whichever is there here. Let's say to give it to all points which are there on this xy plane here. Is this interpretation clear?
Yes, sir. Actually, so I have a doubt.
Yes.
Like, what we do is we sum all of these. Like, we're sweeping this line for varying values of theta first.
Right, right.
Then we change theta, and then we again swipe. So all
Exactly.
these values get added to generate original f of x, right?
Perfect. Perfect.
Yeah.
That's right. That's all that is going to happen here. So that is hopefully now the name also should make clear here. This is a projection. Okay. What you have here are projections, and then you are back projecting them here. And second thing, you are convolving it with a high pass filter also. So that's why they call it as convolution back projection. This is one name for this. You are doing filtering, so instead of calling it as convolution, they will also call it as filtered back projection. Okay, so what you are doing, you have an object, you take different projections here, let's say in this way, in this way. Okay, you got one profile here, you got one profile here, and again I'm not drawing multiple, but you vary it in multiple directions, theta from 0 to pi. For each projection, for this f of xy, you whatever value is there, you go each projection wise, you smear those values here. That's what the word they use it. You back project the values here, and when it comes, suppose if you have here a value of this, so this plus this plus this, everything gets added there. Say for example, if you want me to put some value here, let's say once you projected here, okay, you have, let's say 1 2 3 here. Another projection here might have given you 4 5 6 here. What will you do first as a first step? You put here, when you back project this, that would give you 1 2 3 1 2 3 1 2 3. Okay, that's this one. Now you do this one now, so that means you are going to do it as 4 5 6. What would be the result of it? So add 4 everywhere here, so 5 6 7, add 5 here, okay, 6 7 8, okay, 6 here, 7 8 9. And of course you will have projections in angles also. Let's say this is how you have another projection here. Let's say, yeah, I should be drawing it here, okay, that you take it here, and you might be having a result here for the same. So let me put 1 2 3 4 5 itself. So you do this projection now. So then what would happen? This is 1, so that would take a value of 6 here. Then this is 2, so this will go 2 means 8 and 8. This is 3, so 3 is this, so 10 10 10. And then this is 4, let's say 12 12, and 5 9 plus 5 14. So this is, I'm giving you a discretized version of it. Okay, there's some normalization you have to do. Normalization I have not taken into account, but I'm just trying to explain what the summation operation would mean. Is that clear? Any questions so far? This is the and again this is convolution. You are nothing you are doing in the Fourier domain as such. See, the earlier why we moved there is, if you are taking just the Fourier slice theorem, you have like the samples like this, okay, for varying values of projections. Then you had to at higher values of r, you have very less samples, and to get on a rectangular grid, it is causing you problems, right? That's why here if you look at it, we dealt it in such a way that this interpolation is not at all required. By back projecting your projections, right? And before you project, you are convolving it with a high pass filter as well. So then there are still few more issues to be sorted out. How do you discretize this one? Okay, so well, it is equivalent to what you do. You take m samples of it. Okay, so then you have, then you do normalize it by pi by m. Okay, this is a very conventional thing you do, and it should be quite straightforward. So what you, let me, if you want, I would just quickly write it here. So g theta of x dash, you have it from 0 to pi. Okay, and you have some b theta of, let's say, some xy d theta, you have it. Now you are taking these projections only at, let's say, regular, at theta equal to 0. Okay, and then maybe you are taking n project, some m projections you are taking. Okay, if you are taking m projections, the distance between each projection is pi by m. Okay, the whole thing integral, this integral should give you the same thing as you are varying your, you are taking m projections. And if you are taking m projections, this is equal to pi by capital M into m. Okay, that is your theta value of xy. That's how you are writing it. So now each one is pi by m, so you need to get kind of, the whole thing should be pi, so you would multiply it like pi by m. So that's what would happen here, pi by m into 0 to m minus 1, b of pi by m into m of xy, when you are taking limited number of projections. This is your h of rho. Okay, either you could take the ctft of it, because this is anyway also is rho, so there no, this is also the h of rho only, this also function on the spatial domain is rho here, g of rho, right? So you get it as so what you could do is you take this into Fourier domain. Okay, multiply it and then come back to the spatial domain. That can be done, or else everything can be done in the spatial domain itself, provided you just find out the using convolution by just simply computing the Fourier transform for it. So this is pretty simple. This is the function you have. How could you write this out? There is a rect function if you take it, minus this triangular function. If you do it, you will get this out, right? So rect function, you know, for example, in the frequency domain, if you have a, how could you assume that I am putting a cutoff of plus and minus rho c here as my lower and upper thresholds for frequency, beyond which I would make it to 0. Now my rect function here would be equivalent to rect of rho by rho c here, is it not? This one. So minus rho c to plus rho c. Okay, hope you all remember the rect function. It is by default, it is there from minus 1 by 2 to plus 1 by 2. Since it is there from minus rho c to plus rho c, you will get my rect of rho by 2 rho c here. Okay, and then this is the triangular function you need. This, how could you write this? This you can write it as convolution of two rect functions. But now just the difference would be, this would be, instead of minus rho c, when I am convolving it, it would go, if I am taking this, it will go from minus 2 rho c to plus 2 rho c, right? Convolving this. So I'm making those limits to minus rho c by 2 to plus rho c by 2 here. And then, so this is equivalent to convolution of these two. Then how could I write that? So my h of rho equal to, in the frequency domain, the magnitude I have is rho c. So rho time, rho subscript c into rect of rho by 2c minus, so rho c into rect convolved with rect. So that's equivalent to sync multiplied with sync in the spatial domain. So this is what I would be getting as h of x dash. Okay, yeah, then coming back, this is the summary of the algorithm. What you are going to do, compute gt of x dash for each projection of the object, right? You are taking, so this will give you the projection. Then that projection you convolve with this thing, h of x dash, right? Then you back project the, this is called as filtered projection now, because you are applying this filter now, convolving with this filter. So you now back project the filtered projection by computing. Okay, f of xy equal to this one. That's all that would give you f of xy.
Sir, hello.
Yes, tell me.
Sir, we have the Fourier transform of projection. So from that we are getting the original function.
No, 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 no. We are not at all going into the Fourier domain. That's the beauty here. See, all you have is gt of x dash here, which is all you have here is, see, this is all you have. Gt of x dash is you are taking a projection at an angle of theta, okay, with respect to the sensor. That is all you are doing. You are not at all going into gt of, you are avoiding purposefully computation of just g theta of rho here in a way. Or this you could compute if you want, but this interpolation is what we wanted to avoid. Without going into the Fourier domain itself, you could do everything here. This is just g theta of x prime, that's all. This g theta of x dash. Then you convolve it with h of x dash and back project it.
Yes, sir. Yes.
So what we discussed so far is your projection is in this manner, where all rays are coming parallelly, right? And then at an angle theta, all of them are coming theta. That's not the only way you have projections. And for example, if you are looking at a 2D case, this is called as a fan beam. It's like, yeah, this would be, all the rays would be coming in this manner here. Okay. This again, we are not going to work, but you need to just come up with a method there. You have in the literature now. What if you have a fan beam? How do you reconstruct back? And even more common, particularly in your CT scans right now, if you see, in most of the CT scans, what you have is a cone beam. Cone beam is nothing but your fan detector extended to 3D. Kind of, it will take you along this as well. There is a, yeah, it's like the kind of rays you are coming from your source are like a cone. And then also you could come up, then this apply this, if you want to exactly apply this, you always require beam that is parallel. Then you have, we are not going to work out, but you could extend this work. This serves as the basis. I think if you understand convolution back projection, you could do the rest quite comfortably. Another interesting detail I come across while yeah, preparing for this is this work. In fact, all this thing is done by our Indian scientists, Indian faculty from Indian Institute of Science, G.N. Ramchandran, his name is. And this work has been done in 1971. So this got published in Proceedings of National Academy of Science. So he's the guy, Gopala Samudran Narayanan Ramchandran. He is a student of C.V. Raman. He worked in biology also, in fact, and he has been nominated for Nobel Prize, in fact. He has worked in biology also for his fundamental contributions to protein structure. He has done, he's quite interdisciplinary. So he did in physics, and then he has moved to that. He had worked as a faculty also in IISc Bangalore, and he did his masters and PhD in IISc, and then he moved for some time into Madras University, and later he came back. So this is a very interesting, he has built his own thing there to study the biological structures or something like that. X-ray diffraction and all. I think he worked with Sir C.V. Raman. He's a student of him. And then this is what he did in 1971. But again, independently in a completely different, so they were not aware of each other's work. It's not like Google, you don't have it. This is again astrophysics in a completely different context of fan beam scans in radio astronomy. Okay, so Bracewell and Riddle, they have done it. This is a completely independent works. This happened in fact 3-4 years earlier itself, 1967. Bracewell and Riddle, okay, these guys have also come up with this formulation where they avoid doing things in the Fourier domain, but would which was earlier causing you some kind of blurring effect, by doing this back propagation and filtering in the spatial domain. So it's all right if we don't understand it in the first go. This is not a such a simple thing that has happened just like that. Okay, there is a lot of things that are there to for them to see this. Okay, that's just the detail. I found it interesting, so just wanted to share with you. Okay, so that's all.